So let us continue with our topic of moments and by discussing few more problems. In this example 3.11, a square LMNS has forces acting along its sides as shown in the figure 3.40. Find the values of F1 and F2. So you can see that these forces Fn and F2 in the figure. If the system reduces to a couple, also find magnitude of the couple if the side of the square is 2 meter. So F1, F2, I did not find in this figure. Maybe it is P1 and P2. Okay. Now, in this figure, you can see it is a square. The force 200 Newton, 400 Newton is there. 200 Newton is the diagonal force is there. Okay, and there are two unknown forces P1 and P2 or F1 and F2, whatever you may call this. Now, first we will have to find out the values of P1. We know that if the system reduces to a couple, the resultant force in horizontal and vertical direction is 0. Therefore, the resolving the forces horizontally, we get 200 minus 200 cos 45 degree minus P1. So P1 is in the negative direction. So 200 Newton is in this direction and 200 Newton diagonal force is in this negative direction if we take the horizontal. Okay, so all these things are taken in this equation and P1 is found. And similarly, if you resolve these forces vertically, you have 400 Newton force going up, P2 is going down, 200 Newton is going, diagonal is going down. We'll take the sine component of this, okay, and again by equating this equation, you will find out the value of P2, okay. Um, because the resultant is going to be 0. Now the magnitude of the couple, we know that the moment of the couple is equal to the algebraic sum of the moments about any corner. Therefore, moment of the couple is by taking moment about point L. Okay, so this is 400 into 2 minus P1 because all the other forces moments are coming out to be 0. So this is magnitude of the couple. Let us now discuss the next uh, example, which is 3.3. 3.13, sorry. A uniform rod of weight 250 Newton is hinged at its bottom and B to a fixed point. The rod rests in a position inclined at 60 degree to the horizontal by a string at A in a vertical position. Find the reaction at the hinge and tension in the string. Okay, so hinge is at point B. There is a string at point A which is going up, and you have this weight which is going down at the center point. Okay. Now length of this rod AB. Assume that L is the length of this rod and T is the tension in the string. Now taking moments about point B. So you can take T into this distance which is L cos 60. Okay, this horizontal distance. And then which is equal to 250 into L by because this weight is at the midpoint. So 250 into 1 by 2 of this CB. Okay, and this way you can find out the value of T because L gets cancelled from left hand side and right side both, and T is equal to 125. Now because the forces are all vertical, so we'll find out the vertical component of all the forces. So T plus RB is equal to 250, and because T is known, which is 125, so you can say that RB will be equal to 125. So this is one problem. Then we can discuss the next one, which is 3.18. A ladder rests at an angle of 30 degree to the horizontal with its ends resting on a smooth floor and against a smooth vertical wall. The lower end being attached to the junction of the wall. Okay, the lower end is being attached to the junction of the wall and floor by a string. Find the tension in the string because the surfaces are smooth, especially the horizontal. There is no friction, so support of the string is given over here. Okay, so find also the tension in the string when a man whose weight is one half of the weight of the ladder has ascended the two-third of its length. Okay, so one problem is you have this ladder, its weight is acting at its midpoint. There is a reaction at point B, there is a reaction at point A, vertical reaction, and there is a sting which is giving a tension of T. So by resolving the forces horizontally, RB will be equal to T because only two horizontal, and RA will be equal to W. That is very much evident from this. Okay, and then you can find out the moments also, because we'll have to find out the moment. Okay, and this way, by taking the moments about point B. So this is point B. So this moment for force RB, reaction RB will be 0. For RA, it will be RA into L cos 30, and for W, it will be W into the about point B, W into L by 2 cos 30 degree plus T into L sine 30 degree. T into L sine 30 degree, because T is this, so perpendicular distance will be this. Okay. Okay. So for W, you have to find out this distance. Okay, W into this distance is nothing but this is cos L by 2 into cos 30 degree. Okay, so by this you can find out this uh, tension in the string by putting the value of T is equal to T and W. Okay, so this is RA, taking the moment about point B. So R into this R into, okay, so this is T is found to be 0.866, and for case 2, when a man shows up, M with indicated as M shows the position of the man having weight W by 2, one half of the weight of the ladder. The ladder is in the equilibrium under the action of the following forces: weight of the ladder, weight of the man. Remember, it is 2 by third of L, okay, at a distance of 2 by third of L. Now, considering horizontal forces remains the same, RB is equal to T. Vertically, some W by 2 weight gets added, and again we will have to take the moment and the tension of the string that you will find using the same methodology, except that you will have to count weight of the man also. It is a bit more, 1.446 W. So this is all about the solved problems of this chapter. Thank you.